So hello everyone. Hope you are still awake. So it's my honor to be here to present our work, Multi-Aspect Streaming Tensor Completion. My name is Qingquan Song. I'm a first-year PhD student in Texas A&M University. So this work is co-authored with Xiao Huang, Hancheng Ge, Dr. James Cavalier, and my PhD supervisor, Dr. Xia Hu. To start this presentation, I will give some motivations and definition of the problem we studied. So first, what is a tensor? So a tensor is an n-way array, which is a generalization of vectors and matrices. There are a lot of daily life examples that could be modeled or constructed as a higher-order tensor. To give a small example, we'll look at the problem of personalized expert recommendation. The goal of this problem is to recommend personalized experts of a specific topic to each user. So in this case, we could construct the data into a three-order tensor in which the users, experts, and topics represent the three modes respectively. So each entry of this tensor denotes a user's preference of a specific expert of a certain topic. But in the real-world situation, the data is often raw and incomplete owing to a lot of reasons, such as the maloperations, limited permissions, and some natural drawbacks of the sampling method we use. So this missing data issue inspires us to think about the tensor completion problem, which aims at filling the missing or unobserved entries of partially observed tensor objects. So there is another problem which we may face in the real-world situation, which is called the streaming data problem. So this is also commonly faced in the tensor data analysis, which we call it the streaming tensor pattern. So for example, the roadmap of a city or a country may vary over time. So if we treat each snapshot as a matrix or a tensor slice and put all these snapshots together to form a tensor, so this tensor may generate along the temporal mode over time, leading to a streaming pattern. So the same situation may also happen in a video stream. So each frame of this video could be treated as a matrix of the whole tensor, and the number of the frames may increase over time. So beyond this traditional streaming setting, there's a problem which is more intractable and which we call it multi-aspect streaming. So to explain it, we recall the personalized expert recommendation problem. So in this problem, the number of the users, experts, and topics may all increase over time. So comparing with the traditional streaming setting, so that at each time step, the tensor in the multi-aspect streaming setting could generate along any of its modes rather than just one mode. So combined with the tensor completion problem we have already introduced, so now let's give a formal definition of the multi-aspect streaming tensor completion problem we studied in this paper. So given a multi-aspect streaming tensor sequence with some missing entries, we aim at recovering the missing data in the current tensor snapshot. So this figure gives two consecutive time steps in the tensor sequence. So suppose we have already got a small red tensor at time t minus 1, and it increased to a larger big blue tensor at time t. So our goal is to recover the missing data in the big blue tensor, which is equivalent to recover the incremental part in this blue tensor. So since we already assume we recovered the small red tensor at former time step. So there are a lot of challenges underlying this problem, and we summarize them from three aspects. So the first one is the uncertainty problem. So the uncertainty of the tensor mode changes make it impossible to fix just one or several modes without changing them. And the incremental part is also no longer a tensor if there are more than one mode increase. So the second one is the incompleteness problem. So which means we should not only consider the streaming data pattern, but also we should consider that there is some missing data in this tensor. So the last one is the complexity problem. So this multi-aspect streaming tensor leading to much higher time and space complexity, which is much more difficult for the static model to handle. And it is not a good choice to always reconstruct the static model from scratch at each time step. So to solve these challenges, we propose a general framework MAST for multi-aspect streaming tensor completion. And we also propose a modified model T-MAST based on this general MAST model to tailor towards a special case of this general problem. So now let's go to the details of our framework MAST. So as we know, the tensor decomposition is a very handy tool for the subspace tracking and tensor data analysis, and also solve the tensor completion problem. We first propose a dynamic tensor decomposition method to solve the multi-aspect streaming challenge and also solve the complexity problem to some extent. And then we utilize this dynamic tensor decomposition model to solve the low-rank tensor completion problem, which is the second challenge we have introduced. So then let me introduce my dynamic tensor decomposition model. So this model is based on the CP decomposition. So the CP decomposition is a very commonly used model in tensor data analysis, which aims at decomposing a high-order tensor into several into several low-rank matrices. So for example, for a 3-order tensor X, we can decompose it into 3 matrices A, B, and C. So our dynamic tensor decomposition model is based on a 3-step construction: the partition, substitution, and redecomposition. So from the figure you can see, suppose we got a small red tensor at time t-1 and its CP decomposition. At time t, it increased to a larger blue tensor. And we can first partition the big blue tensor into several subtensors, in which one of it is the original small red tensor. And since we already got the CP decomposition of the small red tensor at former time step, we can approximately substitute it using its CP decomposition. And after this substitution, we can redecompose the whole big tensor and find its CP decomposition. So if we delve into the equations, we can see that the partition step is equivalent to partition the reconstruction arrow between these subtensors and their own CP decompositions. So this xijk represents the subtensor ijk. So the ijk is a binary digit, denotes where the subtensor locates. And since we already got the CP decomposition, and the CP decomposition enjoys a good partitioning character, so we can find the corresponding decomposition for each subtensor, such as we can find the CP decomposition ABC0 for the subtensor X000, which is the former red tensor. And the substitution step is equivalent to substitute this former red tensor X000 using its former acquired CP decomposition ABC tau. So since this substitution may induce some errors, to prevent this error accumulate along the time as time goes by, so we induce a non-negative forgetting factor mu, which is usually smaller than 1, to prevent these things happen. So to understand why the DTD model is faster, we should look at the redecomposition step. So we use the traditional alternating list square method to update these decomposition matrices. And as you can see, based on this substitution, we can avoid using this old red small tensor and also its matricizations. And in turn, we only need to use its former acquired CP decomposition, ABC tau, and which means it's much smaller and easy to handle. And also, based on some basic tensor operation, we can transfer this Cauchy-Roy product into an element-wise Hadamard product, which means it can make the optimization step much faster. So the P and Q is some equations I listed here if you are interested in. So after we have introduced the DTD model, we want to apply it for the low-rank tensor completion problem. So we add trace norm regularizations on the decomposition matrices and optimize it using the ADMM algorithm because it is very useful to accommodate various constraints, and also it is much faster to convert. And to recover the missing data, we use an EM-like approach, which means we fill in the missing entries at each time step in each iteration, and then use the newly acquired predicted values for the next iteration. So after we have introduced the general model, now we talk about a special case and introduce our special T-MAST model. So the special case is when the time is directly be treated as one mode of the tensor in the tensor sequence. So we still use a recommendation system as an example to illustrate it. So the users and the items could be treated at two of this tensor's mode in this case. And since the time is the third mode of this tensor, so this tensor is in fact degenerate to a letter type structure, which we call it a temporal multi-aspect streaming situation. So this is because we do not have a user's information until this user arrives into this system. So the same situation happens to the item. So if we look at the relationship between different dynamic patterns, we can further treat the streaming pattern as a special case of the temporal multi-aspect streaming because when the users and items is not increased over time. So in fact, we can also transform the temporal, each multi-aspect streaming to a temporal multi-aspect streaming by directly adding an additional temporal mode, but this is not what we want to discuss more in this paper. So to solve this temporal multi-aspect streaming situation, if we still want to use our general framework MAST, we should first add some zero paddings to make this letter type structure to construct it into a whole tensor. And then we use the original step like partition and substitution and redecomposition and to find our new CP decomposition. But although these zero paddings won't affect the result in the current step because they are zero, but it will affect the result in the next step because at next time step, we will substitute it using the predicted value in the current time step. So this may cause the accumulation error much more. Although we have already used forgetting factor mu to somehow reduce this kind of accumulation error, but it's still pretty hard because the forgetting factor is hard to choose in the real world situation. So we want to find some other ways besides this way to somehow reduce this accumulation error. So that's why we tailor towards this special case and change our general framework into a special framework to solve this challenge by utilizing this letter type structure. So to compare the difference between the general framework MAST and our special framework T-MAST, we should look at the red part in this figure. So from this figure, we can see that for our general framework MAST, we should first add some zero paddings and treat the red part as a whole tensor and substitute it using the formal acquired CP decomposition. But in our T-MAST model, we don't treat them as a whole tensor. We just treat each tensor as itself and substitute it using its own CP decomposition. So this is like a coupled tensor decomposition, which is different from the original MAST framework, because we don't need to add more zero paddings in it. So for the experimental part, we mainly focus on two questions. The first one is the effectiveness of our framework, and the second one is the efficiency of our framework. We use 4 different data sets to test our model, and the first 2 data sets are general multi-aspect streaming tensor sequence, because no modes in these 2 data sets are temporal mode. And for the last 2, the movie length and Twitter hashtag data set, the last mode of these 2 data sets are the temporal mode. So they are the temporal multi-aspect streaming situation. So we compare our method with 3 different kind of baselines. The first baseline is the static CP-ALS method. It's the CP decomposition with alternating least square optimization. And the second one is the trace norm-based CP decomposition, which could be treated as a special case of our framework when the time step is 1. So it's kind of like a static case of our dynamic model. So the last baselines we use is the OLS-TEC method. It's the online CP decomposition with recursive least square. So this method is originally used to deal with the streaming tensor completion problem. But since to our best knowledge, there hasn't been a method that can handle the multi-aspect streaming situation, we generalize this method intuitively by considering the multi-aspect pattern as a summation of several one-mode change patterns. So then we utilize this method as a baseline. So the metric we use to test our model is first is the running average area under curve, and the second to test the efficiency we use the average running time. So we put partial results here to illustrate our model. And these two figures is to show the evaluation of our effectiveness. So from the first figure is our experiment on the Twitter topic dataset with 80% missing data. So the application is to recommend the personalized expert recommendation problem. So of course, the higher the better. So we can see that our MAST model, which is depicted using the purple line, has comparable performance comparing with the two static models, the TNCP and static CP-LLS models, and also has a higher performance than the dynamic baseline, the OLS-TEC. And from the second figure, the movie lens dataset, the x-coordinates is the time step. So since the first one, the x-coordinates, you can see it's different because the first one we do not have one mode, which is a temporal mode. So the second one, the x-coordinates changed into the time step. And the y-coordinate is still the relative rounding average area on the curve. And you can see that the T-MAST model outperforms our general MAST framework on the temporal multi-aspect streaming cases. So to test the evaluation to test the efficiency of our model, so we show two figures to illustrate the results. And from the first figure, we can see that MAST framework outperforms other three models. And from the second figure, we can see that our T-MAST model shows comparable efficiency with our MAST framework on the short-term datasets. Although on the long-term dataset, we see that the T-MAST model might be a little bit slower than our general MAST framework because it pursues much higher effectiveness, but it's still much faster than the two static models we used in this paper. So to give a conclusion, so we first formally defined the problem of multi-aspect streaming tensor completion, and then we propose a CP-based general algorithm MAST to solve this problem. And we also propose a modifying framework, T-MAST, based on the general MAST model to solve a special case to get much higher effectiveness. And then we empirically validate the effectiveness and the efficiency of our proposed framework. So at last, I will thank for all the Data Lab members and all the collaborators, and also thank for the funding agencies, NSF and DARPA. Without their help, this research is nearly impossible. And thanks for everyone to attend this talk. Thank you.